Hey, can you see the slides? Anyone?
Yeah.
Okay, great. So I'm gonna use some iPad to show that because we're gonna go through a few mathematical details. So in the following lectures, perhaps I will use more frequently the iPads and write something on that.
Can you try advancing the slide just to make sure it isn't like frozen or something?
Yeah. How about this?
It hasn't changed.
Hasn't changed?
No.
Ah, it's bad. How about now?
It's still showing primal and dual forms constraint optimization.
And do you see a new line come out?
Nothing's changed on the slide.
That's too bad. It seems working well on my side. Um, so let me stop sharing and do it again. Sharing screen. Did it show up?
We got primal and dual forms open.
Yeah. And page 23, right?
It has not changed pages. It's in the, oh, now it's moved.
Oh, okay, nice. Okay, great.
Okay.
Okay, so we're gonna release our homework for the second last homework tonight. And don't worry, the workload is not heavy. As mainly focusing on the implementation of support back machines, which is going to finish up today and on Thursday. But again, I would like to encourage everybody to start early and don't rush at the last minute. And yeah, that's it. And let us continue with a support back machine, right? So in the last lecture, we introduced um, the dual form of support back machines, right? We review some like basic knowledge in optimization theory. If you haven't learned that before, that's a good chance to learn that because it's very basic. It's not hard, but it's very fundamental, right? In the future, if you want to dive into machine learning area or optimization area, those are all very basic. And hopefully, our discussion will help you dive into that specifics more easily and naturally. So we introduced the general primal form, dual form, right? We were talking about the constraint optimization problem, right? So usually we can represent the constraint optimization problem in this way, right? This is our objective function, f of x. Want to minimize this f of x, but subject to a set of constraints, right? Each constraint is represented by some inequality. So like G1 x less than or equal to 0 until J big Mx less than or equal to 0. So those represents M constraints, right? So we call G1 and G2 to Gm the constraint functions. So this set of inequalities actually define a region over which we search x to minimize the objective function. Right? So this region is really called a feasible region. Right? So those are determined by this M constraint. Right? So this is general formulation of constraint optimization. Right? So we have shown that this is equivalent to a minimax optimization problem over the Lagrange form. So based on this constraint optimization problem, we can construct a Lagrange function. So Lagrange function is an augmented function, right? Including the original variables we want to optimize and the set of Lagrange multipliers. So for each, so Lagrange function is f of x plus a summation from 1 to big M. Like you have big M constraints, where each summand is a Lagrange multiplier times the constraint function. So I'm showing that this problem is equivalent to a minimax problem over the Lagrange function. And in the inner level, we're going to maximize the Lagrange multipliers with non-negative constraints. And in the outer level, we just optimize over X in the whole space. Like we do not need to restrict X in this weird, probably convex physical region. So the benefit of this minimax formulation is that, so now we only add an extra non-negative constraint. We don't need to restrict X to be in some convex nonlinear boundaries. So in other words, the searching of X is much easier. So this is called a primal problem. It's called primal problem. And we show why this equivalence is correct, right? So it's based on like it's based on like simple reasons. So it's a good insight, but it's not hard to understand. And so hopefully after class you have to review those slides and get to understand because it's very fundamental in optimization theorem. So this is called primal problem. So what is a dual problem? Any idea? What is dual problem?
It's a similar problem, but you switch the minimization to maximization.
Yes, exactly, right. Let's just recall those things together, right? So that I don't need to feel alone, right? Okay, so the dual form is simply switch max min. Right? So dual form is to optimize the same Lagrange function, but in the inner level, we're gonna minimize X in the whole space, right? And outer level, we do the max, right? Max, and again, we need to restrict lambda to be non-negative. Right? So, obviously, the solution for dual form does not necessarily equal to the solution of the primal form. And in general, for arbitrary constraint optimization problem, we actually have this dual form. The optimal of this dual form, optimum value of the Lagrange function in the dual form, are bounded by the optimum value of the primal form. So as to why, it's very easy to show that, and I just skipped the details. So we are interested just to look at it. You just combine two inequalities together, and you will show that. So, and our motivation here. So I'm gonna skip this. I'm gonna skip this. So the motivation here is for SVM. We found an interesting conclusion. That is, the solution for dual form is the same as solution for primal form. In other words, we can solve the dual form in order to get a solution of the primal form. So in fact, the researchers, the pioneers in this area, they have investigated the dual form and tried to derive a lot of things, and they found many interesting insights. And from the dual form results, we can say what do the support vectors mean, right? And what kind of structure can reflect in this in learning linear classifiers with support vector sheets. Okay, so now let us look at the SVM objective, right? So the general SVM objective is also referred to as soft SVM because we can account for nonlinear separable data set, right? So the strategy, the case strategy is that, okay, I do not require my hyperplane to perfectly separate all the positive and negative examples. I allow some examples to break into the margin, right? Well, I just found a majority of the training examples which are linearly separable, and we maximize the margin for that data set, right? At the same time, we allow some outliers to break into the margin. That's the key idea of soft SVM. Want to find such a trade-off. So to allow some examples to break into the margin, we introduce a slack variable Ci for every training example I, right? And then we modify the constraint as that for every training example I, our functional margin is no less than 1 minus Ci, and at the same time, Ci must be non-negative. Of course, if Ci is 0, so the function margin will be strictly will be bigger than or equal to 1. That means, okay, you're staying on a margin or outside margin. But if you can say it's strictly bigger than 0, that means, okay, your example breaks into the margin. That's the connection, right? This is our hyperplane. And for some example, right, suppose this is a positive example. If it stays on the margin or outside the margin, it's here and here, that means this function margin is no less than 1, right? But if it is inside margin, intrude margin, we have KCI strictly bigger than 0. This is how we make our optimization problem more flexible to account for those cases, right? And then in our objective function, in addition to this half square norm of W, we add another term, which is summation over the select variables, and multiply by some constant C, right, which we mentioned before. This is some hyperparameter, which you're gonna need to select by your hand, right? This represents kind of trade-off. So why should we add an extra summation of select variables in the objective? Any thought?
Outliers, to take care of outliers.
Yes, exactly. Right? Thanks, Peter. So basically, if you don't add this extra term, what will happen? Right? So the goal is purely to maximize margin, meaning that, okay, perhaps I'm going to sacrifice most of the examples. I just pick up the most, the farthest 2 points, right? I just find a max margin to separate these 2 examples, right? And all the other examples are just allowed to break into the margin, and the consequence that your training error will grow large. According to our computational learning theory, we have derived before, we know that the true error is upper bounded by both the training error plus some term. So I'm not going to recite the term, but it's kind of VC dimension. Right? The VC dimension function, a term determined by the VC dimension. Right? So that means, okay, if you want to make your generalization error to be as small as possible, right, you not only need to make your VC dimension to be as small as possible, right, you kind of favor simpler hypothesis space. At the same time, you want to ensure the training error is small, right? If you just restrict your search over the hypothesis who can find the largest margin for only 2 points, which are farthest in the data set, the consequence is that, okay, you have a large training error, although you kind of like minimize your VC dimension to the outermost, right? That's not good. Right? That's why we should add this term to trade off the training error and VC dimension term regarding VC dimension. And in the ideal case, we would like to have as few training examples as possible to break into margin. And for the most training examples, we can still be well separated by our linear classifier who has the largest margin. Okay. So this is just a review of our idea. Why should we design a soft SVM objective in this way? Right? So now we're gonna apply our primal and dual form and look into the soft SVM and say objective and say what kind of insights, what kind of results can we derive. Right? So and the following things, right? Although I'm kind of deriving the details with you guys, right? If you don't follow, that doesn't matter because all the results are based on simple calculus and algebras. So I believe everyone is good enough and is feel is kind of practice after your calculus class. So if you don't follow that, don't worry. After the class, just look at the slides and derive by yourself, and you get everything. Okay. So we see that this is the SVM objective function, right? It's typical constraint optimization problem. And then we first converted it to a minimax optimization problem, right? This is called Primal Problem. So then this is our Lagrange function, right? So our original variables to optimize include the weight vector W, feature weight vector W, the bias parameter B, and all the select variables for for every training example, right? And then for each constraint, we need to introduce the corresponding Lagrange multiplier, right? So for the first constraint, for every example, right, we're gonna introduce alpha I, right? So alpha I is, we denote this Lagrange multiplier for alpha I. And for the second constraint, right, we introduce a Lagrange multiplier, which is denoted by beta I. Right? Of course, they're gonna have a beta I non-negative, right? So now we just add them together, we get our Lagrange form, right? So now the question is, why should we put a minus sign here? Right? So this part is our original objective function, right? Copy from here. But what about the second term? Right? The second term, why the remaining terms, why we put a minus sign in front of them? Any thoughts? Any observation? The reason is simply it's not that complex. It's just to conform to the standard form. Remember, when we talk about general convex optimization problem, we're gonna minimize some function and subject to g1x less than or equal to 0, right? Until g big mx less than or equal to 0. So we want the inequality to be like that way, right? This is where the direction of this inequality is, right? So in our formulation of Svm objective, the direction of the inequality is kind of opposite to the standard formulation. So we're gonna change the inequalities. How to change that? We just times minus sign in front of it, right? We get less than equal to, and minus here less than equal to 0, right? And then you just move this to the right-hand side. You got your g1x, g2x, and so on. That's why in our Lagrange form, we need to put a minus sign in front of it, right? So you can see that this is minus ci multiplying with Lagrange multiplier, which is beta I, right? And for each training example, for this Lagrange multiplier alpha I, right? When we will put a minus sign in front of it. When we move minus 1 subtracted by Ci, we get this, right? And then this is a minimax optimization problem. In the inner level, we maximize, given all the original variables fixed, we maximize this Lagrange form with respect to Lagrange multipliers, right? And in outer level, minimize WB and all the select variables freely. Okay, any question regarding this primal form? Okay, yeah. It's just a direct application. You substitute this F and G by I use substitute those SVM objective and constraints for F and Gx to get this primal form. So now, there is some theory showing that, okay, according to the so-called Selector's condition, so I'm not going to cover what is Selector's condition, but basically, the intuitively just saying, okay, if you're doing constraint optimization, and if your feasible region is closed, that means, okay, you must have some interior point in the region. You cannot have all the feasible region on the boundary. Then primal and dual is the same. But this is not required. This is not required in our class, but just to let you have an intuition, right? So we can, according to Selector's condition, we can conclude that, okay, solving this primal form for SVM is equivalent to solving this dual form. Namely, we're going to first minimize and then maximize with respect to Lagrange multipliers. They are the same. And then the remaining things that we're going to look into this dual form. We're trying to simplify this dual form and say what kind of results can we get. Can we further simplify the objective? What other results can we reflect? And then what kind of meaning are they? How to simplify the dual form. Okay. So remember, this is max min. optimization problem, right? So to simplify it, we can just look at inner minimization problem. Sorry, let me use another color. Let us just look at the inner minimization problem. Given the outer level, all the Lagrange multipliers are fixed, right? So if you want to simplify this form, why not we just solve this inner minimization problem given all alpha i's and beta I is fixed, right? And if we can directly derive the optimum value of the Lagrange form, we just substitute into that, and then we can ignore the inner minimization step. That's our idea. And how do we solve that? We just take gradient, right? So first, this is indeed an inner minimization problem. Why? Because this is a quadratic function. We know that quadratic function always has a minimum, right? So it's valid to solve the minimum and minimum optimization problem. And then to solve that, we just take gradient of the Lagrange form with respect to all the three variables we want to optimize, right? So we got a gradient. We need to set the gradient of L with respect to W to be 0, with respect to B bias parameter to be 0, with respect to each slack variable Kci to be 0. Any questions so far? Assume everybody is comfortable with that, right?
Are alpha and beta I hyperparameters?
No, it's not hyperparameter. You want to optimize it. The only hyperparameter is state. You need to set pre-specific value, pre-specified value.
So we need to solve for dl by d beta I and dl by d alpha I as well, right?
What do you mean by D? Oh yeah, DL over D, yeah.
Okay.
So because we're trying to simplify this max mean optimization problem, how can we do that? Right? Let us just fix the outer level where you're gonna fix all the Lagrange multipliers here, right? We just try to solve the minimization problem given alpha I and beta I.
Okay.
And then we'll just take gradient, like set gradient to be 0. Any other question? Okay. So then the remaining thing is kind of quite mechanical, right? I'm not gonna exactly show how we derive this, but it's pretty straightforward. So when we take the gradient of the Lagrange L over W, you see that we have two terms, right? Regarding W, this is this quadratic term, and also a summation over the terms regarding the function margin, right? So if you take the gradient for this quadratic term, you get W, right? You get W here. And that's why we put half in front of it. You cancel the factor 2. And if you take a gradient here, right? So you just go through every training example I, you times alpha I Lagrange multiplier, yi and xi, right? And don't forget there's minus sign in front of it. And if you set it to be 0, you immediately get this. So you can see that the optimum W given any setting of alpha i's, beta i's would be a summation over all the training examples where each summand is alpha I, yi, and the training input xi. This is very important insight. It actually reflects the fact that we can represent the weight vector by a linear combination of the training inputs or training samples. Okay, and then similarly, we just take the gradient of the L over with respect to B, right? Only one term regarding B, right? So you're gonna go through. You have a minus sign in front of it. You go through the training examples I and alpha I, yi, and the gradient of B over B is just 1, right? And you set the gradient to be 0, you get this, right? You get this. So we know that, okay, the summation of alpha I, yi is simply 0. And then the third result will be taking the gradient with respect to CR, right? So you have a 3 terms regarding your objective, right? So this one, and this one, right? So if you take, but they're all linear terms with Ci. So if you set a gradient to be 0, you can get for every training example I, you have an alpha I, so it comes from here. Remember the Ci, yeah, it has a coefficient alpha I and beta I here, and also a constant C here. So we immediately get the summation of every pair of alpha I and beta I is simply C, the pre-specified constant. So the next step will be, okay, we just substitute those results into L, right? Into L, we actually have solved this inner minimization problem, and then we only leave one level maximization problem. So if we substitute the result for W into this, substitute them into L, we get a quadratic function regarding alpha. So as to why, let me just briefly show that because it's really some kind of mechanical. So you know W here is a summation over alpha I, yi, xi, right? So W transpose Wi, that will be double summation. Double summation I, double summation j, alpha I, alpha j, yi, yj, xi, transpose xj. Okay? And then you subtract, you substitute the representation of W for W here, you get minus sigma I, sigma j. So the same thing. You'll find the same term here. So I'm not gonna write it down again. You got a minus, right? So we have a factor in front of it, half, and minus sign in front of it. That's where you get this quadratic term. It's quadratic in alpha values. And then we can apply the results here, right? Summation over alpha I, yi is simply 0, and alpha I plus beta I equals to C. You actually can cancel quite a few terms, and you're going to leave the summation over alpha I only in objective. And of course, after we have simplified the inner minimization problem by just writing down the optimal value, we need to preserve the constraint. Why? Because this constraint, those results actually derived from here, right? You're solving the inner minimization problem is not explicitly reflected in this simplified objective. So we need to keep it. And now the problem becomes one level optimization problem. Okay. Any questions?
Yeah, you might have said this, but where did the J come from?
Where's the J come from?
Yeah, just because we have summation over I in the original optimization, but
so you can write W like this, right? It's just to avoid confusion of indices. Right? You can write W equals to summation over I, alpha I, yix. You can also write it as summation over G, right? So when you do the transpose,
sure.
So you transpose this, multiply with this, right? Otherwise, if you use the same notation about index, they're kind of confused.
Okay, so I and J are going to range between the same values.
Yeah,
it's just
from example 1 to the last example.
Okay, makes sense.
Yeah.
Thank you.
Mm-hmm. Any other question? All right. I mean, this is just let us do it just to practice our calculus. So now we can. I mean, if you want to use some standard library to do that, you would assume you're formulating the problem as a minimization problem. So this is a maximization problem. How can we address that? We can just put a sign, minus sign in front of the objective function, right? Then the max becomes mean, right? So. So we can formulate a minimization problem with respect to constraint. Right? And another problem, we find that in this simplified objective, we actually do not have Lagrange multipliers for beta i's. you see that they are all about the Lagrange multipliers alpha i's, alpha 1, alpha 2 to alpha big N. Suppose N, big N is number of training examples, right? And beta I actually does not explicitly affect the training objective. Beta I only appears in a constraint, right? So for further simplification, why not we just remove beta? How can we do that? So we just replace this constraint by alpha I less than or equal to C. They're equivalent. Why? Because as long as alpha I less than or equal to C, we know that from this constraints, beta I equals to C minus alpha I, right? So it will be non-negative. So in this way, we do not need to keep beta I anymore. And this is our final objective function after we derive a few things, right? In a dual form. So this is a minimization problem of this quadratic function with respect to the Lagrange multipliers alpha i's, right? And subject to two constraints for each I, where alpha I must be between 0 and C, and also the summation over training examples alpha I yi's is simply 0. So this is a typical quadratic convex optimization problem. So there are like a bunch of well-developed mature optimization library that can be used to solve that problem. So we don't need to worry about how to optimize it. Now, homework, we're gonna be able to. We're gonna suggest a few libraries. Like if you Python, you just use scipy, fmin, whatever, and then solve that directly. Okay, any question regarding the formulation here? Is everybody comfortable with that?
Yeah, one other question was just, so if you go back to, so we solved all of those partial derivatives, partial L with respect to W.
This one.
Yeah, and so I guess, why is it then that the partial L with respect to W, that becomes now our new function in that we're going to be maximizing, and the other two functions are just constraints on that?
Oh, no. I mean, we're trying to simplify this maximum problem, right? Our idea is that, okay, let us just fix the outer level, meaning that let us fix alpha I and beta i's. Let's try to solve this minimization problem first.
Right, and so when you solve that, so we're minimizing over 3 separate variables.
Yes.
And so I guess it's just like, I guess it's just a little confusing to me how those like get, so like when we solve that turns into one equation with 2 constraints. Maybe this is just because I'm not as familiar with this. It's like standard with optimization, but.
Okay, so this is like, so we both agree that, okay, if you want to minimize this Lagrange function inner level, we need to gradient, right? And we need to set the gradient to be 0, right?
Mm-hmm.
And we actually did that. And then we substituted the optimal W in terms of alpha I and beta i's with L. We get the optimal value of L, right? But this result is also obtained when all the 3 equalities hold.
Okay.
That's mean, okay, you can substitute to get optimal value of that, but you need to remind the outer level maximization. You must keep all these 3 equalities hold to get to replace L with your optimal value.
Okay, so it's just a combination of minimizing over all of those conditions.
Yes.
Sure.
Yes.
Okay.
Yeah. Otherwise, you cannot replace this whole form by this quadratic form.
Okay, makes sense.
Okay. Any other question? Yeah, I'm happy to see like most people are happy are good with that because this is kind of like a little bit mathematical intensive, but it's really not. It's just you need to write down a few symbols and practice the calculus, nothing else, right? So And why would we care about this new formulation? So we look at the dual form of the support vector machines, we simplify it, and we converted it to another quadratic minimization problem with some constraint, right? So why would we care about that? Right? Although we can use some mature library to do that, right? Why not we just use stochastic subgradient descent that is easy to implement, that is efficient, right? So actually the dual form, this dual form can reflect many other meanings. So we see that, you see, actually the most important thing is that in our dual form, what we care about is inner product between every pair of training examples. This is really important, especially when we extend our linear support linear classifiers by support vector machines to some nonlinear classifiers. Because even you put some like nonlinear mapping to some high dimensional space, right? Say like phi xi, phi xj. The formulation is exactly the same. And we just replace xi xj by phi xi xj, and its inner product is just the inner product after the feature mapping. Right? And we'll see that when the feature mapping is very high dimensional, this explicit computation is very hard, and we can use some so-called kernel trick to reduce computation. That's the meaning why we care about the dual form of SVM. But before we discuss about that point in detail, let us first consider one problem. Right? So suppose I have solved this quadratic optimization problem, right? We get optimal value of alpha I and alpha j, right? How can we recover WB? After all, when we make predictions, we always need some WB, right? W star and B star. We use that to make predictions. Right? The problem is that how can we recover WB? So for W, it is pretty straightforward. Remember when we simplify the objective, when we do the inner minimization, when we calculate the gradient, set gradient to be 0, we have already get that W is always the optimum W is always a linear combination of the training examples weighted by the label yi and the Lagrange multiplier alpha I. Right? And then once we get optimal value of those alpha i's, we just replace alpha I by the optimal values. We get our optimal with vector W star. But then how about B? How about bias strategy? Can we use the same strategy to do that? And unfortunately, the answer is no. Why? Because when we derive the when we simplify the inner minimization objective, right? We have three inequalities. We have three inequalities, right? Partial L over partial W equals to 0, from which we can recover optimal W. But partial L over partial B equals to 0. What you get is just a summation over alpha I for I equals to 0. And for partial L over partial Ci equals to 0, what you get is just alpha I plus beta I equals to C. So those equalities do not contain B. You cannot solve B accordingly. And how can we recover B? In terms of optimal value of alpha 1, alpha 2 to alpha significant. To address this headache, we need to look at another fundamental concept in optimization theory, which is called Kkd conditions. Tucker conditions. So, but here we're gonna introduce what are the Kkd conditions, and from Kkd conditions, what we can derive, and by combining the equalities we just derived, right, and also the Kkd conditions, we can derive B. That's the idea. Right? And Kkd conditions are general for constraint optimization problem. So, but here we just focus on constraint convex program or constraint convex optimization problem because this is the SVM, right? And if you want to know what is the general Kkd conditions for what is the Kkd conditions for general optimization constraint optimization problem, you can find any like numerical optimization book. This is very classical theorem. This plays a central role on that. Right? But again, if you haven't heard of that, that's fine, right? We just give some kind of intro on that. Hopefully, in the future, if you have a chance to go dive into the optimization, they will help you adapt more smoothly. So what is Kkd conditions? So they're just a set of testing conditions for a particular optimization problem. So here we just talk about inequality constraint convex optimization problem. So this problem in general are represented in this way. So we're going to minimize some objective function denoted by f0 subject to a set of big M constraints where all the constraint functions f1 to f big M are complex are convex, and also f0x is convex. And for this particular constraint convex problem, we can write down a set of conditions which are called Kkd conditions. So what are Kkd conditions for this particular problem? That is, okay, we assume there is some x in a n-dimensional space. So n here refers to the dimension of the input. And also lambda, m-dimensional lambda, which corresponds to m constraint here. So we can view that each element in this folded lambda corresponds to one constraint function. The Kkd conditions consist of 4 sets of conditions. So first set of conditions is that, okay, x satisfy all the big M constraints, namely f1x less than or equal to 0, f2x less than or equal to 0 until f big M of x less than or equal to 0. And second set of conditions is that every element of the lambda is non-negative. This is very similar to Lagrange multipliers. Actually, when they are equivalent, lambda indeed corresponds to Lagrange multipliers. But right now, let's just assume, okay, we have a set of such non-negative elements in lambda. And third one is very interesting. This is called a complementary slackness. It's just that, okay, I want for every constraint M, the product of lambda M and the constraint function is 0. So you can see that if lambda M is non-zero, strictly bigger than 0, then this constraint function must be 0. On the other hand, if the constraint function is strictly less than 0, then lambda M must be 0. So that's why it's called complementary slackness. And the fourth set of constraint is that the first set of conditions is that, okay, the Lagrange function is gradient with respect to x is simply 0. Okay, any question regarding the definition of Kkd conditions? Everyone is good? Okay, great. So what can we use? Like, what if we have Kkd conditions in hand, or what kind of conclusion can we draw, right? So actually we can use Kkd conditions to verify or justify if you have arrived at some optimal value. So this is called sufficient condition. So a sufficient condition says if your Kkd condition holds for a particular input x star and some lambda star, then we can claim that x star is a solution to the constraint convex optimization problem, which is defined here. Basically, that it says that, okay, if you kind of find a pair of x star and lambda star which satisfy the Kkd conditions, and then we can claim that x star is the solution to the predefined constraint convex optimization problem. Someone may ask, right, is Kkd conditions also necessary? In other words, if some x star is the solution of your optimization problem, do we exist a lambda such that they satisfy the Kkd conditions? The answer is unfortunately no in general. Only when your constraint functions are sufficiently simple. That's where we're going to discuss about the necessary condition. If your constraint optimization problem, your constraint convex optimization problem, or your constraint has a linear form, is also referred to as affine form. And then Kkd conditions are also necessary conditions to find to the optimal or solution of your convex problem. Meaning that if you find a solution for this particular problem, say x star, right? And then there must exist some lambda star, which serve as Lagrange multipliers, which obey the Kkd conditions. Any questions so far? So they're just a set of testing conditions, right? We can use this testing condition to verify if we have find a solution for a constraint optimization problem. Under certain circumstances, like when your constraint functions are kind of linear, and then you can also use Kkd condition as necessary conditions. Any questions so far? Is anyone good? Okay, great. Okay, so now we can apply this results, right? And see if those sufficient or necessary conditions are applicable to our problem. So actually it is. Actually for our SVM formulation, Kkd conditions are both sufficient and necessary. Why? Any thought?
The constraints are linear in our case, so probably that's why it's necessary.
Yes, exactly, right? We just take a look at this, right? We just contrast it to our formulation, right? All the constraints are linear to WB and CI, right? So of course, we can arrange them to have this form, right? So fortunately for SVM formulation, right, the Kkd conditions are both sufficient and necessary. That means, okay, when we solve them in the dual form, right, when we get alpha stars, those solution, right, we know that there must exist Lagrange multipliers in W and B star, they jointly satisfy the Kkd conditions, right? We're going to use Kkd conditions to derive or recover the optimal value for B, the bus run. Okay, let us do it, right? So we're going to mainly use the complementary slackness in the Kkd condition, namely that for the optimal values of beta i's and slack variable CI's, those corresponding constraint, right? We know that the product of each Lagrange multiplier and the constraint function is 0, right? So for every training example, we have this beta I star times CI star is 0. And also for another constraint, right, we have this alpha I star times the function margin subtracted by 1 plus KCI star is 0. This directly comes here, right? So according to the complementary slackness, when we get a constraint function here, we know that the alpha I star times this constraint function at the optimal value is 0, right? So similarly, we get this beta I star times this KCI star simply 0. This is where this is just a application of the complementary slackness in our problem. And then we're going to combine the zero gradient result when we simplify the dual form, right? Remember when we simplify this max-min optimization, namely the dual form, right? When we take the gradient of L with respect to W and B and KCI, we get 3 equalities, right? Now we're going to use the third equality, where for every example I, the summation of alpha I plus beta I equals to C. Right? Let us just place the 3 results together and see if we can derive the optimal B, right? So the first two comes from the complementary slackness in the Kkd conditions, where for every training example I, we have the optimal beta I star times Kc I star is 0. And then second complementary slackness for every training example I, we have the optimal alpha I star times this guy, simply 0, right? And when we solve the dual, we have a third part comes from deriving setting the gradient of the objective function to be 0. We get alpha I star plus beta I star equals to C, right? Now we put them together, right? So how do we use these three results to derive B? If you look at the optimal values for alphas, right? Alpha 1 star, alpha 2 star to alpha big N star. Remember, suppose we have a big N training examples, we have a big N alpha values. Right? The number of alphas is the same as number of training examples. So why not we just find some optimal value of alpha j, who is strictly between 0 and C. Remember, in our optimization problem, when we simplify the maximum problem, we have a constraint that for every alpha j, it must be between 0 and C, right? We have this equality as well, right? But here, when we solve that problem, we just pick up some alpha j star who is strictly between 0 and C, and then check where we can get, right? So first, because alpha j star is strictly less than C, right? And then we know beta j star will be minus C minus alpha j star, right? Which is strictly bigger than 0, right? Because alpha j star is strictly less than C. And according to this complementary slackness, beta j star is not 0, right? And then we have to have this slack variable Kc j star to be 0. Right? And then if we look at the corresponding second complementary slackness, we know, okay, this part is simply 0. And meanwhile, because alpha j star is strictly bigger than 0, so look at this complementary slackness again, right? This term is bigger than 0, and then we only have this term to be strictly 0, right? So we got this guy is simply 0, which is the function margin subtracted by 1 and plus Kc star, right? And from our previous derivation, we know that Kc star is simply 0, right? So just to get rid of it, now we have only left W star and B star. W star have already been recovered. And then we can immediately get the B star, the optimal value of B, which is to subtract the label Yj by the inner product between the optimal beta vector and the input vector Xj.
I have a question about this.
Uh-huh.
So why not just like we've done in some of these other, like in the perceptron algorithm or whatnot, we combine the B as in W, and we just put that as the last value in that vector. Why do we not do that in this case? Just because then in that way, it seems like then you could get B star as just your final value in that vector.
Yeah, we can do that for sure.
Okay, but this is an explicit solution for B star, in just as a separate standalone variable.
Yeah. You can use the like notation simplification trick we mentioned before, right? We fold P into W, but the problem is that when you do the when you derive the dual form, when you simplify the form, I'm not sure if you get the similar results. I'm not mean to say that it is not feasible. I will encourage you to try that.
Okay.
Yeah, but here I just want to give you a solution on that, and this actually reflects some important things I want everybody to know. I'm not
cool.
Any other ways of doing that.
Sure. Okay.
Okay. So someone asked, okay, there might be multiple alpha j stars which are strictly between 0 and C, right? So each one we can get a B star, right? So in practice, to make the result more robust, we often average the results over such j, meaning that over those optimal alpha j's who are strict between 0 and c. Any other question? Okay, so but here I want to supplement one point, right? Although in practice you can always find some alpha j star which is strictly between 0 and c, but in case that in some particular data set you have all alpha j stars either equals to 0 or c, what can we do, right? Seems like we cannot apply this chain of derivation to get b star. How can we do that? Here we propose another general solution to that. Just look at the primal form. Right? So if you still remember the primal form, which we use the subgradient descent to address that, right? So we actually eliminate all the constraints, right? You have a regularizer plus involves, right? Max 0 y minus yi w transpose xi plus b, right? Sorry, it should be like that. Right? So in case that you don't find such alpha g star, which are straight between 0 and c, right? And we can go back to the original objective function we have addressed, right? So now we know w star, right? So the problem is only to solve this b, right? So you can use the custom gradient as well. So, but in practice, in most cases, you can simply find something in between and use that to recover. You don't need to go back to the primal form and eliminate constraints and do the optimization here. Any questions so far?
Can
Is
we
that
also, for alpha j, rather than putting the constraint that alpha j should be less than equal to c, if we put a hard constraint that it should be always less than c, then it will always follow, then we'll be able to find b for every case.
Oh yeah, but how to justify you put a strict constraint? Right? It's actually, you will find that. I will arrive at that point in a minute. Actually, you'll find that many alpha g star is simply 0. Of course, I mean, if you change the constraint to be more strict, right? I require every alpha j to be strictly between 0 and c. Well, of course, you can do that, and you don't need to worry about you don't find such alpha g star, right? But you need to justify the that why is this valid, right? Actually, this constraint with equality on both sides, or both ends, are important, and we'll explain right now.
Okay.
Okay. So now we have use the Kkd conditions. We have derive something related to max mean. I mean the dual form as Svm. We found very interesting result, right? We also know, okay, once I solve the dual form, how can I recover optimal W star and B star, right? So now let us look at the structure of the solution. Right? So from the dual form, what we can get is that, okay, we know that the W star, the optimal wave vector, is actually a linear combination of all the training inputs, right? So it's over summation over alpha I star yi times xi, right? Yi is either 1 minus 1. It doesn't change the skew, but the skew is determined by the Lagrange multiplier alpha I star, right? So then a natural question will be, what if some alpha g star is simply 0? If alpha j is simply to be 0, then the corresponding sample xi, xj, yj will not affect the weight vector at all. In other words, our weight vector, optimal weight vector, is only determined by those training examples with non-zero alpha G stars. Right? And we refer to those examples who have a non-zero alpha G star as support vectors. This is where the support vectors come from. Why they are called support vectors? Because only support vectors determine the final weight vector for the classification. Any questions so far? Is everybody comfortable? Okay, so now let us, one curious question will be, okay, where do the support vectors locate, right? Are all training examples will be support vectors or just a few of them? It turns out only a few, although the training data can be very large. Right? In practice, there are only a few examples will serve as support vectors, which determines the final weight vector for classification. Okay, so how can I see this, right? So let us denote the set of support vectors by S, right? S is consists of all 10 examples whose corresponding alpha G star is strictly positive. So we know that our optimal or final weight vector is a summation, is a linear combination of the support vectors weighted by the alpha G stars, right? So we know alpha G star bigger than 0, right? According to the complementary slackness, remember, the Lagrange multiplier multiplying with the constraint function must be 0, right? At the outcome. And that means, okay, this guy must be 0. This guy must be 0 implies that your function margin is 1 subtracted by the slack variable Kkd star. And we know that Kkd star is non-negative, right? So that means, okay, your function margin is less than or equal to 1. Right? So what does that mean?
So is that support vectors are the outliers, kind of like outliers in that epsilon j constraint?
Yes, exactly. Right. So actually, this result we derive from complementary slackness explicitly show us that the support vectors can only be those outliers which either stay on the margin or inside margin. That's interesting, right? You kind of like you separate most of the training examples. Those examples are staying outside margin, right? And you allow as few examples to break into margin as possible, and your support vectors are only determined by them. So another question is that what if a support vector stays inside margin? If it stays strictly inside margin, it means that, okay, this one is strictly less than 1, right? In other words, the Kkd star must be strictly positive, right? And if we look at the complementary slackness again, right, we know that one result is that beta G star, Kkd star is 0, right? This guy is strictly positive, then this guy must be 0, right? At the same time, we know alpha G star plus beta G star is C, right? So beta G star is 0, meaning that alpha G star is C. What does it mean? Remember, the final weight vector is a linear combination of the support vectors, right? Each support vector is weighted by this alpha G star. And alpha G star is maximum value of alpha G star is C. Right? That means, okay, the larger the alpha G star, the more important the support vector. So if your support vector stays strictly inside the margin, that means the corresponding weight or coefficient is the maximum, meaning that it takes maximum importance. What it can reflect is that, okay, it's indeed those outliers even fail to classify points determine our final classifier in support vector sheets. Any question? Okay, great. So now let us give some concrete example, right? To be more intuitive, right? I just showcased an example. So here are the positive examples. Let me use this right here. Positive examples. Here are here a negative example. Here positive examples. This black line is our hyperplane, and the red lines indicate the margin, right? So this is margin. This is a margin. So if you want to look at where the support vectors locate, first, all the examples which stay outside the margin won't be support vectors. Namely, their optimal value of alpha i's are simply 0. Support vectors can only be found in those examples who stay strictly on the margin or inside the margin, or even your classifier misclassifies them. And in practice, you'll find that because we always want most examples to be perfect separated, right? By the large margin classifier, that means most examples whose alpha I star is simply 0. If you want to store the weight vector, you only need a few support vectors. Any questions so far?
Can we modify this by saying that this is actually an outlier detection? Like anything for which alpha is greater than 0 is supposed to be an outlier to a certain class.
Yeah, of course, because this is derived from the complementary slackness. We know for any support vector whose alpha J star is strictly positive, right? So we must have this equality host means that your function margin must be less than or equal to 1. Any other question?
So the subset of vectors that are going to be support vectors, that could essentially change as it's trying to, like when it solves this optimization problem, obviously it's like, yeah, well, I think, never mind. I think this makes sense just based on this picture.
Yeah, just want to show you where the support vectors stay, but that does not mean all the outliers like intrude the margin or stay on the margin will be support vectors. Support vectors can only be a subset of them. It's not necessarily mean that as long as it is an outlier, it will be a support vector. There is no guarantee of that. Only guarantee that, okay, if your examples stay outside the margin, they are not support vectors.
So really the idea is just that the W star is just being influenced by the points that are essentially close, that are I don't know the best way to put it, that are closest together, the hardest to classify, the ones that are going to like, I don't know the best way to put it, but you have all these big, what we're saying is a lot of these training sets are going to be easily separable, but those aren't influencing how we're calculating this. It's just going to be based on the small subset where it gets tricky to separate.
Yes, exactly. Okay. Yeah. So that's the fabulous things where this optimization result reflect, right? So I mean, what we do is just to use some like common ordinary tacklers and algebraic operations, we get this fancy results. That's why when support vector machines were developed, they kind of like it's a big wave. Like people immediately throw out neural networks and look at those things, right? Because it's so elegant. It is justified by computational learning theory. They have very good explanation of that. And also later we'll say it is very easy to extend to nonlinear classifier by combining with kernel tricks. Okay, so now we have finished the discussion about dual form of support vector machines, and from which we know what support vectors really mean, right? So now we're going to jump into a second topic, right, which is important. It's called kernel method and kernel tricks. And by using kernel tricks, we can extend support vector machines to complex nonlinear classifiers. Right? So if we want to predict with the dual solution, how can we do that, right? So our prediction rule for linear classifiers is always like this, right? So we calculate the prediction score, which is a linear function, W inner product between W star and pass the input X, and plus the bias parameter, and then look at the sign, right? And from dual solution, we know that okay, the final weighted act is actually a summations, a combination of the training inputs, right? Of I star, of course, we can exclude those non-zero support vectors because they don't have any effects on that. So non-support vectors because they don't have any effects, right? Let's just assume, okay, we can write W star in this way, right? And now if we substitute the representation for W into the prediction function, right? What we can get is that we will calculate inner product in the prediction score, right? W star transpose X, right? So we're actually going through every support vector and then calculate the inner product between the support vector and the test input X, right? So we see this inner product again. Right? This is actually the case to generalize to nonlinear classifiers. Why? Because when we use the dual solution to make predictions, we actually do not need to explicitly write down W. We only need to calculate the inner product between every support vector and the test input, like test example. Even if we perform some nonlinear mapping. So suppose in order to improve the generalizability of the linear classifiers we mentioned before, the trick is to perform some nonlinear mapping, right? Map the original feature vector to a higher dimensional space, where we expect that in a higher dimensional space, it's much easier to be separated by linear classifier, right? So even we perform some nonlinear feature mapping or high dimensional feature mapping, right? When we can apply the same kind of framework to solve the dual form, and then use the representation of each vector in terms of support vectors, and then substitute them into the prediction function to make prediction, which you only need to calculate inner product again. But before the inner product, we need to first do the feature mapping and then do the inner product. This is just a review of our previous idea, right? So suppose your original input vector is two-dimensional, right? To make it linear separable, we can conduct some nonlinear mapping to map the feature vector into a four-dimensional space, and then in this four-dimensional space, we learn which vector, right? For linear classifier, right? So we can apply exactly the same formulation, same optimization procedure to learn that after the feature mapping. So now, suppose we want to do this, right? In order to make your data mostly or almost linearly separable, right? We want to first perform some nonlinear feature mapping, and then during the prediction, we know that we're gonna calculate inner product, right? So let us define this is a function. This is a function of the two original inputs, x and z, right? The calculation, the function value is to first perform the high dimensional feature mapping, and then do the inner product. And then during the prediction, right, we can simply, when we solve the dual form, right, when we replace w by its representation in terms of support vectors, we got our prediction function in this way, right? So it's alpha I, yi must belongs to the support vectors, right? And now this is essentially phi xi transpose phi x, right? So it's now we represented it by a function of xi and x. Okay? Is where we get, right? So we can rewrite our prediction rule in this way. And what's the meaning of this, right? If we explicitly compute this, right, compute this function. Namely, if we want to compute the k of x and x, every time we need to first perform the nonlinear feature mapping and then calculate the inner product, it means nothing, right? It's just a notation replacement, right? It doesn't show anything. In other words, if we have to compute this feature mapping every time explicitly, we gain nothing in computational advantages. But the challenge is that you'll find later, if we want to really improve the generalizability of our linear classifiers, you need to choose a really high dimensional feature mapping. Like suppose it is 1 million dimensional. Suppose your original feature space, your input is only 10 dimensional right now. You want to map it to a 1 million dimensional feature vector. And if we explicitly compute this function, like mean that okay, you're first gonna map them into two 1 million dimensional vectors and calculate inner product. It is very costly, right? Very costly. A natural question would be, for some particular feature mappings, do we have a simplified way to compute this inner product after feature mapping? In other words, can we just compute this function in the original feature space, but the result is the same as we explicitly perform feature mapping in a very high dimensional space and then calculate inner product? If the answer is yes, we can reduce a lot of computation, right? We can reduce a lot of computation, and this is something we gain, right? So we call this kind of a function as kernel function. Any questions so far?
Do you mean to say that we do this kernel trick on the fly? Like, or
So basically our motivation is that, okay, I'm gonna come out some kernel function which does not require us to calculate this explicit feature mapping and then interpret that. Then our training and prediction will be much easier and much cheaper. Much cheaper.
okay.
Does it make sense? So I want to showcase an example, right? So I mean, if we just say that abstractively, it's kind of like not very clear, right? So if we look at this example, right, which is called Nominal Kernel, right? So suppose we're given two example x and z, and we want to map them to the high dimensional space, for example, quadratic space. And then in the mapped feature space, we run some small vacuum machine to find a linear classifier. Right? How can we do that? This is how we perform mapping, right? So that is just to get all the degree 0 term, degree 1 terms here, and degree 2 terms. Right? So the degree 2 terms are just the cross product between every feature, right? So you see x1 square, x2 square, xn square, x1, x2, x1, x3, until you enumerate all possible combinations, right? So if you count how many features in a mapped feature vector, it also will be like proportional to n squared. But in our original feature space, you just have an n-dimensional feature, right? So you can imagine that if n just equals to 1,000, then after feature mapping, you have to deal with 1 million dimensional feature vector, right? So every time if you explicit do the feature mapping and do the inner product, it is very costly, right? So we can show that like explicitly performing this quadratic feature mapping and then have an inner product, which will be take O n squared, right? Is the same as, so where is it? Calculate this kernel function. That is, you just calculate inner product between x and z in the original space, n plus 1 takes square. You see that the computation of a kernel function still lies in the original feature space, right? But the result is equivalent to performing explicit feature mapping here and then do the inner product. The complexity of computing a kernel function is simply O n, right? But if we do the explicit feature mapping and do the inner product, I will take O n squared. So you can see it's a dramatic reduction of the time complexity. Does it make sense? Any questions so far? Okay, great. Let us stop here, and on Thursday we'll continue with the kernel tricks, and we'll show why this and this are equivalent, right? And then we'll talk about the properties of kernels, and then how do we insert kernel trick into the dual formulation of the support vector trees. Okay, see you on Thursday.